Right, left. I did it on purpose. What?
I was playing with you. It's.
I don't know how to. I don't have you. It's all already here.
I like that. I'm sorry. It's the third one, but it's more protected. I don't think it's.
If I get run like today.
Like a.
Or not on these shoulders, like they get. Like I don't know.
I might have actually gotten like a.
No.
If I did it, I would use this stuff.
I was yesterday and I know they failed. It's so fun.
I don't, yeah.
Other find the number of holes in each other.
Yeah. It's so obvious.
Yeah.
So, one graham cracker was one graham, so it was definitely.
Okay, we're moving along, in our packet.
But it's a new.
So page 11, we'll do, complex number review, but then we need to start 7.05, so we'll just get as far as we can. But I think you'll find this pretty, much, a review, and what we're gonna see with the next section, it just feels like you're building on top of what we've already learned, so. All right, so, just need to do a little bit of review in terms of, the algebraic portion of dealing with, imaginary, number I. The special property here is that I squared is equal to -1 to allow for, us to take the square root and get a negative number, or, square something and get a negative number, so we can have that, ability. So, I is just equal to I squared is equal to -1. I cubed is basically I times I times I, so it's I squared times I. So if I multiply these two together, I get -1I, yeah. And I to the fourth would just be I squared times I squared, -1 times -1, which is 1. So it's just going to keep cycling through these possibilities. It's either, and then when I to the fifth, it goes back to being I to the sixth, I to the seventh, I to the eighth. So, you know, with these larger numbers, rather than having to look at it, start from scratch, we have a much more efficient way of getting to what like I to 724th is without having to count from the beginning. So we use this property that we use in the calculator. We divide the exponent by 4, and whichever remainder we get, that is going to indicate which pattern is going to fulfill. It's either I, -1, -I, or 1. So here's the pattern. If I get a remainder of 1, that's going to be indicated by 0.25. So if you divide something by 4, and if you get 0.25, that indicates that it's going to fulfill this, it's going to match this pattern, this I here. If you divide a number by 4 and you get a remainder of 2, or rather, if you get a 0.5, 0.5 means remainder of 2. The remainder of 2 is going to match this -1 here. And if you divide your number by 4 and remainder 3 would be represented by 0.75, and 0.75 is going to match with -I. And if you get no remainder, that means there's no decimal, then it's just going to be 1. Okay, so let me just show you what that looks like. We could count to 11. That's not too bad, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it should be -I, but we can also confirm that. If I do 11 divided by 4, look at the decimal there, look at what comes after the dot, 0.75, 0.75 matches with -I. So
the last remainder you have? What does that say?
Oh, no remainder. So if you get so if it divides out evenly perfectly with no decimal afterwards. Yeah, so we'll practice that. So for instance, 11, right? That's my number. I divide my exponent by 4. And I get 0.75, so 0.75 indicates it's going to be negative I.
So the whole number doesn't matter, just like 0.7.
Yeah, just look at what comes after the decimal, right? Okay, so 18, we could count, but it's easier if we just divide using calculator. 18 divided by 4 is 0.5. Right? And 0.5 means that it's second pattern in the rule. And that's one. Okay, 67 divided by 4, we get a remainder of 3. And we can indicate that by seeing that 0.75 there.
0.75.
Which one?
Like, before you said you like earlier 3, now it's real 0.75.
Oh, so that's the rule. Yeah, so if you were to divide it out by hand, 67 divided by 4, you would get 127 times 6, 24, remainder of 3. So remainder of 3 is on negative I, but in the calculator, it'll show you 0.75, and you can recognize that as negative I. Okay. So 724, either we do it by hand or we do it using the calculator. 724 divided by 4, 181. So that means it divides out evenly, therefore just 1. Okay. Standard form for a complex number takes on the form of a plus bi. Complex number has 2 parts. It has the real part and has the imaginary part. The imaginary part is the one attached to the I. The real part is the one that's by itself. All right, so these are just very simple review here. A lot of times you're going to treat I like you would a variable. So we're just combining like terms here, adding them together. -4 plus 2 is -2. 7i minus 3i is 4i. Careful with the negatives. Just have to make sure you distribute the negatives through. Seven minus 4 is 3. -12i minus 9i is -21i. Let's do 13. 13 is multiplication, so you would just FOIL like you normally would, and then if you multiply 2 i's together, you get I squared, and at the end we can clean up the I squared. So I'm just going to FOIL this out. Yes. FOIL this out. Okay, so negative 24 plus 6i minus 32i plus 8i squared. Now, these three terms are, well, I can combine these two, but I can, if I ever see I squared, I can always clean this up. I know I squared is the same thing as what? Negative 1. So negative 1 times 8 is negative 8 or minus 8. Right? So now we have some like terms that we can combine a little bit easier. We have negative 24 and negative 8, which is negative 32. And 6i minus 32i is negative minus 26. Okay, so really the only additional step you have to take other than that's different than before is that you got to deal with I squared, right? So you have to clean up your I squared and combine it with the constant that you see. Let me skip down to number 14 here. Two factors that are exact same multiplied together, just like a binomial square. Like this. Number 15, two factors that only have a sign in the middle changed. These are called conjugates. So if I want to find a conjugate of 3 minus 5i, I would just say 3 plus 5i. And the interesting thing about conjugates is that they have a special way of removing the I in the problem. So for instance, if I were to multiply this out, this will come out very clean. All your imaginary portions will go away. So a lot of times we use that conjugate method to help us clean up a denominator or a numerator. So let's just try 15 here and see the nice thing about a conjugate. Again, if I want to create a conjugate of a binomial, I just write the exact same term. I just change the sign in the middle. So 3 plus 5i is the conjugate of 3 minus 5i. Likewise, if I want to find a conjugate of 3 plus 5i, 3 plus 5i's conjugate would be what? 3 minus 5i. Yeah. So these are conjugates of each other. And if you multiply conjugates together, you can see that your imaginary portion will just disappear. So let's try to see. Okay, so 3 times 3 is 9. 3 times 5i is 15i minus 15i minus 25i squared. 15i, negative 15i goes away nicely. We know we can convert this 25i squared be negative 25, but it's already a negative here. So I squared turns into a negative and the two negatives cancel out. So I get 9 plus 25. 34. So just want to show the nice thing about conjugates, anytime we involve conjugates, is to get a side or an expression cleaned up. Okay, so that's what I want to show you on this first page. Let's go to the next one. Yeah, we're just going to speed through 7.04. It's just a review so that we can understand the parts that's going to come up in 7.05. All right, so this is easy, right? State the conjugate of the given complex number. So what's 9 plus 4i's conjugate? Yeah, so it really is that easy. You're just changing the sign that you see in between. Okay, 5 minus 2i's conjugate is 5 plus 2i. Negative 3 plus 7i. Yeah, so you're only changing one sign. Don't change other signs. All right, so it says use the conjugate of the denominator to rationalize the following fractions. So we can use the conjugate to help us get that 5 minus 2i, get that I in the denominator to basically shift up to the top. So what we're going to do is we're going to multiply by the denominator's conjugate to the top and to the bottom. And I can do that because if I multiply the top and bottom by the same expression, I'm essentially multiplying by 1. I'm not changing the overall value. So what's conjugate of 5 minus 2i? 2i plus 2. So make sure that your numerator and denominator look exactly the same. We don't want to do the conjugate of 1 plus I. We only want the conjugate of the 5 minus 2i because our goal is to get that I to move up to the top. So this is the way to do it. Okay, so now we're going to FOIL everything out. Top with top, bottom with bottom. So 1 times 5 is 5. 1 plus 1 times 2i is 2i. All right, do some cleanup. The denominator should clean up nicely for us. 4i squared, the same thing as -4, negative, and the negative will be a positive. So 25 plus 4 gives me what? 29. And in the numerator, the middle terms combine, 7i. This becomes a -2, so 5 minus 2 is 3. So this is acceptable, but if you sometimes the problem wants you to write it as a plus bi separated, so you can write it as 3 over 29 plus 7 over 29 I. It just allows you to see that a plus bi a little bit more cleanly.
So the i's not in the numerator or not.
It's in the numerator, but you can always push it out in front outside. So 7i over 29, the same thing as 7 over 29 times I. Typically, I like to see it in this form. It just feels more familiar to me, but you can write it as 7i over 29 if you want. All right, try number 20, see if you can go through that process and practice this particular skill. Okay, multiply the top and bottom by -3 minus 7i. Right, FOIL out the top and the bottom. Any questions with 20? Okay, so we have something called a coordinate plane, but we also have something called a complex plane. All you do is just understand that your x is your real number, and then number line, and then your y is your imaginary number line. So all that's saying is that you're just going to plot your order pair like you normally would. You just treat whatever's in front of I as your y value and whatever's by itself as your x value. So this is the same thing as plotting for -3. And then it says find its absolute value. So treat this like you would from the previous section with magnitude, which is Pythagorean theorem solving for your hypotenuse. So here, absolute value of 4 minus 3i is the same thing as saying, okay, what's the distance between these two? Distance from 0. But really, you're just going through Pythagorean theorem, right? So square root of 4 squared plus 3 squared is 5. All right, so treat this like magnitude, like how you would with magnitude. Okay, let's go through these real quick here. -5 minus 5i. Okay, check these other two here. All right, procedure feels very familiar from previous unit. Okay, just a quick review. Let's go into 7.05. Okay, so we're going to do a quick review of complex of a rectangular to polar form, and then we'll bring in the complex numbers. But it's just really going to feel familiar to involve I. Okay, so bit of review here. Everybody good with this page? Okay, so find x and y. I know I can use sine and cosine, right, to find my x and y. So that cosine of 5 is equal to x over 9. Cross multiply, solve for x. If I want to solve for y, I can use Pythagorean theorem. I can also use sine. All right, sine. Cross multiply. Okay, from vectors, for a bird flying 20 meters west and 35 meters north, find the resulting magnitude and direction. So I need to draw this out. West, that's left. 35 meters north. We'll associate west with negative because we're going left. Right, just like how you were able to show on the vectors test. If I want to solve for theta, I can use inverse tangent. To find magnitude, I can use Pythagorean theorem. inverse tangent b over a or y over x. But we have to make an adjustment, right? This is second quadrant, so how do I get this into the second quadrant measure? Yeah, involve 180. Okay, so we're just doing a bunch of review as a way of showing how this is going to connect immediately with what we were to see before. Okay, so from polar coordinates, convert. Okay, so convert this order pair into the polar form. So if we have x and y, and if we want to get to r and theta, same process, right? Same as above. Right, Pythagorean theorem, get you your magnitude, and then inverse tangent. Which quadrant is this in? Third, so I got to involve 180. Right? Okay, all review so far. All right, so for complex numbers, it's going to feel the same. It's just we have to involve I and understand that I is really kind of like your quote unquote your Y value. So in rectangular form, A plus BI. Think of A as your real number, B as your as associated with your imaginary unit. Think of A as your X value. Think of B as your Y value. The real is the X axis and the imaginary is the Y axis. Okay. Absolute value of a complex number known as modulus, which we've been calling it magnitude, but it's the same process. It's just ignoring the I and then just doing Pythagorean theorem. Imagine you're just finding hypotenuse. So everything feels familiar, right? 8 minus I, same thing as 8 comma -1. And then just find their Pythagorean theorem. Again, when you go through this process, you ignore the I. Just understand the I is to help you identify the Y value, but you're not going to involve I. So imagine this 8 minus I is just 8 -1. You're just plotting that order pair. And you're just using these numbers to help you get to your modulus or magnitude. And this value tells us how far we are from the origin. Yes.
The magnitude we've been doing.
Yeah,
again.
same process. We just have to just interpret it from a different perspective, but it's the same process. Mm-hmm. Sorry?
Where's the first example? At the bottom.
Oh, bottom,
Eight
yeah.
mice.
Yeah, root 65 and 3 root 5. Okay, everybody good with this page? All right, page 14. Okay, so page 14. Okay, we'll skip the investigation. We already know the formula. Oh. This is just based off of the distance formula. So if I want to find distance between two complex numbers, then here's the formula here. So d is equal to the absolute value of z sub 1 minus z sub 2. And it's basically the distance formula that you've seen over the years. So you take your real components, subtract them, a sub 2 minus a sub 1, square it, and then your imaginary components, which is the coefficient in front of the I, combine those together. So let's say we have these two complex numbers, 5 minus 3i and negative 1 minus 8i. It's the same thing as saying find the distance between these two ordered pairs. You're just putting the x's together and putting the y's together. So, and you're not going to use I, okay? The I is just to help you identify what is the quote unquote y value. Okay, so square root. You take your real components, subtract them. So I'll do negative 1 minus 5. And then second, negative 8 minus negative 3.
Negative 1 minus 5, does that mean it'd be z2 minus z1? So
Oh, sorry, this is to indicate this is the notation for the distance between two imaginary numbers, two complex numbers, but you're going to follow this formula here. Let me show you a different way of doing this. If I want to find distance between two numbers, I can just subtract the x together and the y's together. So I can do 1 minus negative 8. Okay, and then 7 minus 4, which is 3. Oh, I'm sorry. The formula says z1 minus z2. My bad. Let me change that again. Okay, we're getting the same distance formula. We just kind of follow a different form here. So z1 minus z2, so negative 8 minus 1, negative 9. 4i minus 7i is 3i. And if I want to get from this form to distance, I can just treat this like how I would with the Pythagorean theorem, square root of a squared plus b squared.
It's supposed to be A1 minus A2.
Yeah, it should be a1 minus a2. Well, z1 minus z2. So
Yeah, but that's right.
right. Yeah, so if I do z1 minus z2, that just means I am subtracting the like components, putting it together.
Same thing.
Same thing, yeah, same thing, just different presentation. Okay, so another common uh, skill that we've learned is learning how to find the midpoint between 2 points. So very similar here, midpoint formula. We would associate midpoint as adding the x's together, finding the average of the x's, finding the average of the y's, and that's your midpoint. So same thing here, it's just that now you're kind of finding the average of the real component and then finding the average of the imaginary component.
Use I divided.
Right, the I is just used to help you identify what coefficients to use for the y or for the imaginary portion. So the midpoint formula between two complex numbers is just z1 plus z2 divided by 2. So in other words, I can add the real components together between the two complex numbers, add the imaginary components of the real numbers of the imaginary of the complex numbers together, and then divide by 2 for each of them. So imagine I'm just trying to find the average of these two numbers. So 5 minus 1. And then my imaginaries together. So -3 minus 8. So I'm still going to leave my ordered pair as complex form, standard form. So this becomes 4 over 2, which is 2. 11 over 2i. Yeah, I can say plus -11 over 2, or you can say minus 11 over 2i. Okay, so try number 4, see if that makes sense to you. So average the real components together and average the imaginary components together. Okay, so just want us to practice with these few skills. On page 15, I just want us to do just 3 problems here. Do number 3, number 5, and number 9. 3, 5, and 9. Give you guys a few moments to try that, and I'll put the answers up. Take only a few minutes, I think.